Hello, welcome to this vignette on linear regression assumptions. We'll primarily use visual inspection and the CAR package in R for checking regression assumptions, but there are many other resources to do this in R. For example, the RMS and the GV-LMA packages are nice. The major assumptions that we make in linear regression are: we assume that there's a linear relationship between the independent variables and the dependent variable. We assume that our residuals are normally distributed. We assume that there's little or no multicollinearity between independent variables, that there is no autocorrelation, and that the error terms are homoscedastic across the range of fitted values. And we'll treat each one of these in turn. So for the linear relationship, each of the coefficients in our model should be a constant value. We can model nonlinear relationships, but the terms in our model must be linear. This first model is going to be a problem since there is no fixed value for beta 2 that will fit the relationship. We have this squared term here that's going to be a problem. In the second model, we're going to include this squared term for x2, and that will fix the problem, because then we'll have a constant value for each of the coefficients in the model, and we'll satisfy that linear relationship. This code will show us some component residual plots that we'll use to visually inspect the two models for adherence to our linear assumption. So component residual plots are one way to see if the predictors have a linear relationship with the outcome variable. The red dashed line in the figures represents the best fit of each predictor and the residuals. And the solid green line is a running smoothed average along the x-axis. And as we guessed before, beta 2 is violating our linear assumption. This green line should follow the red dashed line, and it obviously doesn't. There's this very clear quadratic relationship that we are not capturing in that model. Now, these component residual plots look much nicer in the second model. Another thing that you can use these component residual plots for is to visually inspect which variables are contributing to your model. Here we see that beta 1 and beta 3 look like they have non-zero slopes, but the slope for beta 2 is quite flat. If we looked at our summary for model 2, we'd see that the coefficients for beta 1 and beta 3 are probably statistically significant, but the coefficient for beta 2 is probably not going to be. Just another way that we can visually inspect that relationship. Now, for the multivariate normality assumption, there are a couple ways that we can look at normality. The Shapiro-Wilk test for normality will give you a quantitative measure of whether your results are normally distributed. And the QQ plot will give you a graphical way to see what's going on with your residuals. We're going to fit two models here to show good and bad examples. The first model has random normal error terms, but the second model has error terms from the t distribution with 3 degrees of freedom. This is going to look almost normal, but it has fatter tails, and it's going to violate our assumption. So we'll fit the models, each model here, and then when we run the Shapiro-Wilk test, we'll see how they look. The augment function, just to look at the code here a little bit, the augment function will give us a data frame with the original data that was used to fit the model, and it'll be augmented with some fitted values, residuals, and other handy statistics from our model. The Shapiro test takes our studentized residuals here that are returned by the augment function, and it will perform the normality test we're looking for. Now the Shapiro.test will be loaded automatically with the standard R unless you start it with vanilla or something. It's in the stats package. The augment function here is in the Broom package. Now the null hypothesis is that the residuals are normally distributed. So a low p-value is a bad thing. It's clear that model 1 with the higher p-value performs much better than model 2, which has this very small p-value. And that model 2, again, with the t-distributed error terms, is violating that normality assumption. Now if we look at the QQ plots, this function here comes from the car package. There's a lot of different QQ plot functions. I like this one though. The QQ plot here looks pretty nice. What we want is to see all of the points fairly close to this line here. And certainly they should be pretty much all between these two dotted red lines, that area in there. So this one looks really nice. When we look at our other model, we see that there is a pretty good deviation with it coming down here and up there. That shows us the extra fatness of the tails, that they're too spread out. The variance is too high. Now for our next assumption, we assume that there's little or no multicollinearity. When independent variables are correlated, our model can become unstable. The coefficients change a lot depending on which terms are included in the model. These variance inflation factors give you a measure of how much the residuals are inflated when each predictor is added to the model. This is compared to the full model minus the predictor in question. And this can give you an idea for what predictors might be correlated with each other. In this example, we see that x2 is a function of x1 right here. So they're going to be very highly correlated. When we look at the full model, including both x1 and x2, we see these variance inflation factors that are quite high for x1 and x2. As a general rule of thumb, we should be concerned if we see anything over 2. If we drop one of them from the model, then the variance inflation factors should drop back down to about 1 for whichever one is left in the model. So if we drop x2, the variance inflation factor for x1 should drop back down to about 1. The next assumption we'll discuss is autocorrelation. Autocorrelation most often occurs when there's a correlation between observations at regular intervals. For example, hourly temperature tends to cycle between a daily high and a daily nightly low. There's plenty of variability, but if you know yesterday's high, that will tell you a lot about what today's high might be. So in this example set, y is a function of x1, but there's also this cyclical relationship added in. We've got the sine of x1 that we're adding into the model. Now if we plot the data, we can see this sine wave coming out in the data. You see this sort of wobble back and forth that's very consistent as x1 changes. This is a clear violation of our no autocorrelation assumption. Now, the Durbin-Watson test can give us a measure of autocorrelation. Again, the null hypothesis here is that there's no autocorrelation, so small p-values are bad. And this model, by this test, obviously violates our assumptions. We have a small p-value, and we can then reject the null hypothesis and assume that there is, in fact, autocorrelation in our data. We won't go into how to fix and appropriately model a data set like this, but there are some good resources on the web. If you Google linear regression with autoregressive errors in R, there's lots of great examples of how to do that and discussion on that. So the last assumption we make is that the error terms are homoscedastic. That is, the variance of the error terms is constant as the predicted value increases. So this is a nice example here. The relationship between y1 and x1 is going to look just like what we're used to, but when we plot x1 on y2, the variance is going to be very small around 0 and get larger as x1, and thus x2 increases in magnitude. So we'll go ahead and plot these two data sets to take a look at this. As we expected, the relationship between x1 and y1 looks beautiful here. We have this nice football-shaped scatter around the trend line. And the error terms look fairly, the variance around that line looks fairly constant along the line. This relationship, however, looks pretty bad. As you can see here at the lower end, that the variance of error terms is very small. They're all very close to the line. And as we move out, the variance increases, the spread around that line increases a lot. Perhaps a better way to view this would be with a spread level plot. So this figure shows the fitted values on the x-axis and the absolute standardized residuals on the y-axis. So we can see as the fitted values increase down here along the x-axis, the variance of the residuals is also increasing. They are a little closer together here, and then they become very spread out as we get up over on this end. This is more what we would expect when the homoscedasticity assumption is not violated. We may have a few points, kind of only a few of them down here. More of the data are up over in this area. But it looks like they're reasonably spread out. And the red trend line here is pretty much flat. That indicates that the variance along here is remaining very constant. We can also test this quantitatively with a non-constant variance score test, like this. Now these results shouldn't be surprising at this point. Remember that the null hypothesis, again here, is that the error terms are homoscedastic as the fitted values increase. So model 1 has a nice high p-value, indicating that null hypothesis, no evidence to disbelieve that our error scores are not homoscedastic. And then model 2 has this very low p-value, very small p-value. And so we reject the null hypothesis and we say there is good evidence that our homoscedasticity assumption has been violated in model 2. Now we can transform y2 to the fourth root scale, and we get something that's much better behaved. You could also use a log transformation. In this case, that's not good because some of our values, our y2 values, are less than 0, so they'd be dropped for the model. But when we do our test for homoscedasticity here, we get a much more reasonable p-value. It looks like this model is not going to have as bad of a problem with that assumption. And again, this is the transformation here we do with y to make it look a little more to even that variance around the line out a little bit better. So that brings us to the end of our discussion on testing of linear regression assumptions. Thank you for watching.